We present learning a decentralized multi-arm motion planner, a scalable planning approach for large multi-arm systems. Sampling-based approaches, like rapidly exploring random trees, are the go-to solutions for motion planning. However, their runtime scales exponentially with the dimensionality of the configuration space, so it may run efficiently in a 2D maze, but it may not in a multi-arm system with 3 arms. A multi-arm motion planner should be scalable, in that its runtime scales efficiently with the number of arms in the system. It should be flexible, in that arms can be added to, removed from, or moved around the workspace without an expensive retraining of neural networks. It should be cooperative, in that all arms need to reach their targets in a collision-free manner. Finally, if we want it to work in dynamic environments, the planner should also be closed-loop, so that it could react to unknown dynamics of objects. We achieve scalability by treating the multi-arm system as a cooperative, homogeneous multi-agent system. A single policy, which observes other arm states and outputs a closed-loop delta joint action, is shared between all arms and trained using multi-agent reinforcement learning. We achieve flexibility with an LSTM state encoder, where the observations of other arms are treated as a sequence and processed by an LSTM to extract a fixed-size encoding for the motion planning policy. We incentivize arms to cooperate with a team reward, where each arm is rewarded only when all arms in the system reach their targets. However, this makes the reward sparse. To address this sparse reward problem, we guide the policy's learning with expert demonstrations from bidirectional RRT computed offline for the task dataset. Then, during training, if the policy fails on a specific task, the corresponding expert demonstrations is supplied along with its failed trajectory. Otherwise, the policy will only see its successful trajectory, which allows the policy to improve through self-exploration beyond the expert. Our final policy is able to maintain high performance for easy, medium, and hard tasks as the number of arms scales, where different difficulty levels measure how tight the workspace is. Now, we show some results at these difficulty levels. Despite being trained on only 1 to 4 arm tasks, our policy is able to perform well on 5 to 10 arm tasks. Our policy can also directly generalize to dynamic tasks while being trained on only static tasks, thanks to its closed-loop formulation. Meanwhile, as the configuration space grows, BiRRT fails to plan efficiently to reach dynamic targets. Now we show some comparison to the baselines. In difficult planning problems, arms must reach their own targets while ensuring that they do not block other arms from reaching their targets too. Therefore, it's not enough that only a single arm reaches its target in a collision-free manner, but all arms must do so in a reasonable amount of time for the task to be successful. Lastly, we show our policy's application in a 6-DOF pick-and-place task. Here, by supplying target poses to its motion planning policy, we can control the arm to reach its pre-grasp pose or pre-dump pose. In fact, any task that can be described by a sequence of end-effector poses can be used in conjunction with our planner, which allows arms to do different high-level tasks while being controlled by the same low-level policy. Thanks for watching.